So, sharpening our view of Earth processes with high-resolution topography. So this shows two views. One is sort of the fundamental data set would be a surface, like a digital terrain model or digital surface model. You can see the disruption of the topography by the surface rupture of the Denali earthquake. Another representation of the data are point clouds. And so these would be maybe more fundamental data sets in the sense that you need a point cloud to produce the digital elevation model. And here, this shows the kind of true 3D representation of the Earth's surface as well as the nearby vegetation and anthropogenic features. So this is a point cloud from, airborne point cloud from the Granite Dells, which is a place where one of my students worked on precariously balanced rocks up near Prescott, Arizona.
Are these both LiDAR? Can you point out when they're structured for motion?
Yeah, these are both LiDAR. So this is an EarthScope LiDAR data set. This is an NCALM seed grant data set, but both airborne data. You can even tell a little bit on here, just you see the lines of the scan lines for the laser scanner. And this is probably a 50-centimeter digital elevation model. This just shows kind of contributions from lots of people. Some of them are here. And so this is just trying to show that, this constant issue of scale, because you could say, well, why did you come to this course? What's the deal? It's one of the biggest deals is spatial resolution. How big is our ruler, or how smaller is it? What size features can we represent? So on the right, this diagram, this is showing the area of the El Mayor Cucupa earthquake, and this would be 90 meter per pixel shuttle radar topography data. So it's kind of useful at a regional scale to show the Laguna Salada and the adjacent mountain range, but we really aren't going to talk about the surface rupture with these data. The line red shows where the rupture went. But now with airborne, so 1 meter airborne laser scanning data that Mike Oskin and I worked to get after the earthquake, we can start to see the surface rupture coming through. And you see the 90 meter pixel from the above data set, it would completely span the rupture. You couldn't even represent it. But with the 1 meter data, we can definitely represent the rupture. So this illumination is coming from this direction. So we have this, the illumination is coming from this direction. So this is a east-facing scarp right here. And you see really rich fluvial landforms as well. And then you can zoom in even closer. So this is a 10 centimeter per pixel terrestrial laser scan from Peter Gold, going down to sort of the actual fault scarp scale and secondary fractal on why, and a little bit on measuring topography. And then we kind of really emphasize the issue of scale. And then these 4 bullets here are fault trace mapping, reconstructing slip history, understanding geomorphic response to uplift or differential surface displacements, and then 3D topographic differencing. So these 4 bullets are how I sort of divide up how we use these data for faulting type research. And there are many other applications in ecology, vegetation, other geomorphology, but this is just kind of over the last few years I started trying to classify, well, where does this study go and where does that one go? And I've started dividing up into that grouping. And so we'll kind of go through applications. So then just a little bit of kind of big picture science community. In the last decade, we've really seen a lot of interest in high-resolution topography in many science communities. And so these are just kind of books and studies that have been written that say how we need these data, and then also how we need to be able to figure out how to handle them and reuse them. So if you use them once, can we use them again? So elevation for the nations, this is a floodplain mapping. This is landscapes on the edge, so this is the sort of future of surface process research. This is new research opportunities in the earth science. It's a very big guiding document for especially the National Science Foundation. New challenges and opportunities in hydrologic sciences. These communities, so EarthScope, which is helping to support this meeting, but also seismology and geodesy, mention the value of high-resolution topography for studying earth processes, including faulting. And then even the USGS sponsored a study by Dewberry as part of an effort to kind of move towards high-resolution data for the whole U.S. So I think you were saying about how you would wish that we had high-res data for all of North America. Well, there's long-term thoughts about it. So this is a 3D elevation program by USGS. So it's like working toward it, but it's quite expensive.
I can say more about it tomorrow morning.
Okay. So example scientific motivations. How do geopatterns on the Earth's surface arise, and what do they tell us about processes? How do landscapes influence and record climate and tectonics? What are the transport laws that govern the evolution of the Earth's surface? So these would be pretty basic kind of geomorphic questions that come from landscapes on the edge. If we're into ecology, we could have questions like, or statements about a coupled hydrogeomorphic ecosystem response to natural and anthropogenic change, landscape and ecosystem dynamics, scaling, model parameterization, linkage to in-situ observations, integration with other remote sensing data. So this is a big push in ecology to really use these data as well. So sometimes the parts we throw away, like the vegetation in a point cloud, are really what the ecologists most care about. And so, you know, this is a view, this is a figure from something called the critical zone, and so, which is a project as well as a concept. And that is that really the critical zone is kind of the piece of the Earth that goes from the top of the vegetation to the bottom of the roots. And so that means the topography between them, and we care about all of that. And if you're a geomorphologist, you care about it because of the surface process. If you're an ecologist, you care about it. And if you're into faulting, you care about it because your faults are ripping through this. And these processes also remove the record of faulting over time. Questions? Okay, so here's this little animation of sort of thinking about taking apart topography into some components as it might develop. So we have some initial elevation field. So initial elevation is a function of space. And so maybe there's a little channel cutting through. Let's say we displace it. And so we add to that initial topography some tectonic displacement, some vectors that move the topography so we get a little offset. And so we might see something like this, where we have the initial topography, these fluvial features on this alluvial fan, and they were broken by the earthquake. But we know that there's geomorphic displacements that kind of erode this sharp topography and smooth it. And so this tries to show how there's kind of sedimentation in this little trough, and then there's erosion on the shoulders. And so over time, we begin to obscure the tectonic displacements by the effect of the geomorphic displacements, which change elevation by actually moving mass over the surface. And so here's an example. This is a structure from motion model from the balloon that Barrett built. And here we're seeing offset stream channel. We see this is Phelan creeks in the Carrizo Plain. We've San Andreas and Skier, these drainages come across, have sort of 15 and 20 meter offsets. But then you see over longer time, there are additional offsets that we were interested in, including this one's about 220 meter offset. But it's degraded. Its ability to sort of record that offset has diminished over time, although not by very much because it's so clear. But we start to worry about this geomorphic displacement causing us to lose the tectonic signal, or the challenge of sort of seeing through it. Now, if you're a hardcore geomorphologist, you're like, I don't really care about the tectonic displacements, just give me these. But either one is valued. So then, in the end, we have the sort of current elevation as sort of the sum of these fields. And surface processes act to change elevation to erosion deposition, while the tectonic ones depress or elevate the surface directly. And sort of a related concept for some of our work is then we look to identify geomorphic markers, which would be landscape elements for whose geomorphic displacements, meaning erosion and sedimentation, are small enough or understandable enough that the tectonic displacement can be interpreted. So for us, mostly in this room, since mostly are interested in faulty, this is one of the things we would be looking for. So questions on that? Okay, so here's a little bit of something we worked on with Andrea, which is, talking about topography. What do we need, especially when we talk about earthquakes? And so we need topographic data with sufficient spatial extent and resolution to capture the phenomena of interest, but we may also need it with sufficient temporal repeat to capture changes of interest. So, we'll talk about different things, especially tomorrow, but it'd be really nice to have topography before the Darfield earthquake and then after, and there was some. But then, it's not only do we want to get this sort of co-seismic signal, and I know somebody mentioned they were interested in creeping section and afterslip. We want to know not only what happened co-seismically, but then also what happens after the earthquake. So, for example, in Napa, there was quite a significant additional amount of deformation after the main shock. It would be really nice to capture that, but it occurs kind of in a log T time scale, and so it's happening rapidly after the main event. So just a little bit on extent, what we need is, let's say here's a huge earthquake occurring in western China, the Cocochile earthquake. It was 430 kilometers long, and you see it rip the ground really spectacularly. So this is the other challenge. It's one thing to have fine spatial sampling, but we need it over large spatial extent. So this is a big sort of data challenge for and that might be why one might want to go in space. Thing on scale I'm going to be talking about for a little while. This just shows kind of changing sort of pixel sizes. And this is 10 meters per pixel, so broadly, it's kind of like, I got new glasses recently. It's like, oh, maybe I did need new glasses. And then you put your glasses on, you see, so much finer, bringing things into focus, right? And that's basically going from 10 meters per pixel to 50 centimeters per pixel. So we get the big features still. We can tell that the landforms are there and the main elements are represented, but the fine scale is not. We're sort of lumping together different processes. And this is trying to show here on the right the drainage area. So basically above each pixel, how many pixels are there that might put water to that pixel. This is computed in open topography using our TAUDEM tools, which Chris will talk about a little bit later. So you can see that in order to represent the fine scale of the drainage network, we need a fine scale of the digital elevation model. And this representation here would not be able to show us these fine features. Now, if we're not interested in that, it's okay. But many times you are, because the fine scale transition between the fluvial and hill slope systems is a fundamental part of the landscape, and we need to be able to identify that transition. And so that's why I think that there is really a critical scale length, which is around a meter per pixel. Finer than that, we really are in business in terms of geomorphology and earthquakes. Coarser than that, and we start to not be able to really see what we want. I'll talk about the scale thing for a while. So here's the other thing about the earthquakes is this is Wells and Coppersmith, so this is kind of classic earthquake scaling, we would say. So this is basically earthquake magnitude on this side versus some geometric part of the rupture. So the first one is surface rupture length. So the longer the earthquake is, the bigger it is. So here's the thing is earthquakes of interest, let's say societally and also for big tectonic applications are above 6.5, maybe 7 to 8. And so there we really are looking at 100-kilometer long ruptures. So we need big data extent. But also, if you go to average displacement, so how much are some features offset? For magnitude 7 to 8, we're sort of in this 1 to 10 meter range. But as we go to finer or smaller earthquakes, we're sort of mapping into smaller surface displacement. So again, we need that sort of finer resolution of about a meter, but over 100-kilometer length scales. And so here's just one example of also an important thing we started seeing in almost like a data competition. So this is aerial photography differencing before and after the Landers 1992 earthquake from Chris Milliner. So this is a GQ paper. And so this is not topographic data, but we want to work towards being able to do this. And we've done a little bit of it, and Ed will talk about this probably tomorrow. But basically what you can see is you can really see the discontinuity of the main rupture, which is we know how earthquakes work fundamentally. But what's really of interest then, so these are the horizontal displacements in north-south. and then these are east-west displacements. And so we looked at air photos from before and after the earthquake and used this software called Cozy Core to basically compute what are the best matching displacements to kind of match up the features in these air photos pixel by pixel. But it's 2D. It doesn't have the third dimension. So that's one thing where some of our topographic differencing will help us to get the full 3D displacement field. But one of the things that Chris was able to show is that as you go across the fault, let's say XX prime, all the deformation isn't at the fault. It's on some finite width. So we see off-fault deformation as well as on-fault deformation. And this becomes really interesting for sort of fault mechanics, is being able to measure that sort of proportion of on and off-fault deformation and realizing that maybe some of the offsets we're studying aren't giving us the full sort of deformation that might go into a budget. Okay, so that's kind of an application that we might work towards. And again, need a time scale. So here's the thing about time. So some of you mentioned this, but this is from the 2004 Parkfield earthquake. And we went out, so Kay's advisor at Utah Valley University, Nathan Tokay, worked with me for his PhD. And so Nate and I worked on this. We mapped all the cracks right after the earthquake manually. And this is topography we measured with a surveying instrument, total station, so not nearly as good as what then came like a year later. But what we can show was that right after the earthquake, there was maybe a couple of centimeters of deformation, but over time, there was the main shock displacement, but there was this significant afterslip that continued to tear the ground. And this is really interesting to capture, but it kind of decays over in this case, it's kind of long-lasting, a couple of weeks at least. And so being able to measure and then remeasure to capture that is a really big technical challenge. Actually, we're not quite able to very well yet, but I think we'll start seeing, and those of you who with your SFM experience, next time there's a big earthquake in California, we're all going to scramble. We'll have co-seismic, we'll get this, but then we'll start doing this and getting this full 3D displacement field post-seismic or after slip will be really amazing, but quite challenging. Okay, so any questions just on that sweep? Okay, so then just kind of coming back a little bit to data, so the big challenge is getting the right coverage and time, space, and resolution for the question.